Hello everyone. So we already have discussed um, different concepts related to PN junction. PN junction again is a device. It's a diode. We explained what is a PN junction, the structure of PN junction, and most importantly, we discussed the band diagram, energy band diagram of PN junction under equilibrium in forward bias condition, in reverse bias condition. We also have discussed the concept called breakdown. What happens in breakdown or during breakdown? Why breakdown takes place inside a semiconductor PN junction device? The concepts associated with other concepts associated with this has also been discussed. Now, in this lecture, we will cover two very important concepts. One is small signal model of PN junction. So, we will see what is a small signal model, why it is important, and how actually small signal model will help us in analyzing or in different engineering problems related to PN junction. We also will discuss diode capacitance, which is very interesting and very important concept, because if you look at the PN junction, across the junction there are two different types of charges. In one side it's p type, another side is n type. It creates a depletion layer, and then you get major one type of charge majorly accumulating in one side. The opposite charge is accumulating on the other side. So all these charges actually will give you a effective capacitance effect. Now, what is that capacitance effect? Why diode capacitance is important? What does that signify? So all these concepts you will see in this lecture. So let us start the lecture and go through these concepts, and we will then understand what is small signal model and what is diode capacitance. Let us start.
So we already have seen some of the details regarding reverse and forward bias junctions. Now today we will start the equivalent circuit and the small signal analysis associated with PN junction diode. So for that purpose, let us begin with the basic circuit that we consider. So in this case, what we do is we consider a very small signal voltage applied along with the DC bias, and then we calculate the current passing through the diode. So the small signal that we apply, the voltage signal, can be given by V is equal to Vm sine omega t. So this is an AC signal, and the magnitude should be small. And we consider that the magnitude or the amplitude of the small signal or small AC signal should be much less than Vt, that is the thermal voltage. And that is why we call it a small signal analysis. Similar studies we already have done in analog circuit course, that is there in the already I have uploaded those lectures. So you can go to that analog circuit course and can figure out the details regarding small signal analysis. However, in this case, we also will try to see the small signal analysis from the device perspective. So the small signal voltage is given using this equation V equal to Vm sine omega t, and the associated current small I is equal to Im sine omega t plus theta, where omega is the frequency and theta is the phase difference. And the equivalent circuit for a PN junction diode can be given using this circuit, where resistance and then capacitance is in parallel. This is the diode equivalent circuit. So as we progress, we will see what is the reason behind this circuit consideration. And another important thing in this case is we will take quasi-static analysis in our consideration. Okay. So let us first figure out what is a quasi-static small signal model. For that purpose, let us connect PN junction diode, which is P plus N in nature, as we already have said. Also, we have done different analysis using this P plus and diode, and then we connected this with a voltage, and you will find that a current is flowing through it. So in this case, let us connect the voltage in forward bias. Okay. Now you have seen that in my previous equivalent circuit, I have shown the resistance and capacitance both are in parallel. So one of the major reason behind considering both the components in parallel is the same V here is actually responsible for the current as well as the charge. So as we discuss, we will, or the matter will be more clear, that the same voltage is responsible for the current and the charge or change of charge inside the PN junction. That's why we consider both the resistance and the capacitance in parallel, because in this case only you can have the same voltage that is acting for both resistance and capacitance. Now in this case, as we already have said, the applied voltage V is responsible for your current. Now if you increase the voltage by a small amount, that is dV, then you will find a corresponding change in current, which is di. So you can consider V plus dV will lead to a I plus di. And while we are changing the voltage, the entire system will take some time to stabilize. So we will consider that we are waiting up to that much time when the entire system becomes stabilized. Now the voltage V also leads to a charge or change in charge that is stored inside the PN junction. Now if you change the voltage from V plus dV or from V to V plus dV, if you change by an amount of dV, you will find that the change in the charge has already influenced. So the extra charge for dV voltage is considered as dQ in this case. So the resistance R can be given by dV by di, and the capacitance C can be given using dQ by dV. So in this case, we will take a modulus of this particular value, because Q can be positive or negative. However, the capacitance value should be positive in this case. So we will consider a modulus of dQ by dV while calculating the capacitance associated with that. So I hope this is already clear that once you have a V, there will be a flow of charge. Now if you change the voltage by dV, so you can also expect a change in the flowing charge, which is dQ. That's why we said that this V plus dV will also cause a charge Q plus dQ. Now we know that under forward bias, the equation of the current is I is equal to I0 into e to the power V by Vt minus 1. Now from here, if you calculate di by dV, which will be I0 e to the power V by Vt minus divided by Vt, and this also can be written as I plus I0, because this minus 1 plus 1, if you do, then this particular term will lead to the equation I, and then you will have another I0 if you multiply I0 with this particular expression. So you will have I plus I0 term, or from the equation also it is very clear, this can be written as I0 into e to the power V by Vt plus I0, minus I0, right? And this is what is your I. So I0 into e to the power V by Vt is nothing but I, if you take this I0 that side, plus I0, right? So that's why this particular term can be written as I plus I0 and then divided by Vt. So your R value is dV by di. So di by dV is nothing but 1 by R, which is equal to I plus I0 divided by Vt. Now under forward bias, this I0 value of I0 is very small. So you can consider this approximately as I by Vt. So your R will be approximately equal to Vt by I for forward bias. Now, under reverse bias, we know that the current I is nothing but minus I0, right? We already have seen this is the reverse saturation current. Now, under reverse bias, we will have minus I0 plus I0, that is 0 by Vt. So, that means under reverse bias, your R will be almost equal to or tend to infinity. If we consider the reverse bias voltage to be greater than 3 Vt, right? So your R will tend to infinity, which is the case for ideal diode, both of these. However, in practice, you know that with applied voltage, your reverse bias current also changes. There is a slope. We already have discussed that thing. Your reverse bias voltage also changes because of the generation recombination current. For reverse bias, it is generation current, right? So in that case, your R will not be infinity. Rather, you will find a very high value, maybe hundreds of kilo ohms in the reverse bias condition. Okay. So this is what is the value of R for your diode. Now let us see what is the value of capacitance. So the resistance value is very clear in this case. However, let us see the capacitance values. Now, in order to estimate the capacitance, what we have done, we have drawn the space charge as well as the neutral region or the excess carrier concentration in the same diagram. So you can see here I have shown both majority and minority carriers in the linear scale. That's why we put a cut here, because otherwise it is not possible. We already have discussed these things, why it is not possible, because the amount is very less, and in linear scale it is very difficult to show both of them. So this one is for your excess carrier concentration, and here we have space charge concentration. Now, when you apply voltage, then your space charge region or depletion region shrinks, right? And when it shrinks, your quasi-neutral region, that is this region, will expand. That we already have seen. So this dotted line that you see here is for V equal to 0, that is equilibrium condition. Now the moment you apply voltage, it will shrink till this point, right? And why it is shrinking? Because there are extra charges that is coming in the quasi-neutral region, and that is actually reducing the depletion region. And this extra charges, for example, in P side it will be extra holes, in the N side there will be extra electrons. Although there will be extra electrons in the P side as well, but as extra electron in P side will be very less because it's minority. That's why we are not considering those. We are only considering the majority carriers in this case. So you can consider the most of the charges that is coming in the quasi-neutral region is actually extra hole. So this particular area is actually showing you the extra hole, and in this case this particular area is representing extra electrons, right? Now this extra hole and extra electron will shrink the depletion region. Now under forward bias, you have seen there is a change in electrons and holes compared to the equilibrium. Now this particular change in the charges actually lead to a capacitance, because capacitance is nothing but dq by dv. Capacitance is nothing but dq by dv. dq means change in the charge. And what leads to the change? That is the extra charges that is coming in after applying a bias or potential. Now this change can be due to the change of space charge width, or the change can be due to the change in excess charge in quasi-neutral region. So there are two possibilities. So one is the change in the space charge because of the space charge width, if you change the space charge width, or this can be because of the change in the excess charge in the quasi-neutral region, and these particular changes will lead to a diode capacitance, as I have said, which is dq by dV. There are impurities in the diode, but the concentration of impurities are fixed. So there is no contribution of impurities for the capacitance. You can consider the contribution from the impurities are negligible. Now, if you look at the quasi-neutral region, you will find that the extra hole concentration is compensated by the extra electron concentration injected by the negative terminal in the negative side. Okay. So these are the concentration plot for electrons and holes in both the sides. Now this extra hole concentration is due to the injected holes in the p side that is there, and these will be compensated by the electrons in that particular side. So if you look at the entire picture, that is majority and minority excess carrier concentrations, you'll find the entire system is charge neutral. So that is how it becomes easier to explain why the entire system is charge neutral when there is an extra charge present or excess carrier present. So this particular diagram helps us to get that particular understanding. However, in this case, we need to figure out the charge or the change in charge, and then we will do dq by dV to figure out the capacitance. Now let us take the space charge region in consideration first. So we have two regions, one is space charge region, another one is quasi-neutral region. Let us start with the space charge region. Now in the space charge region, we know that there are extra holes and extra electrons that has come into the picture, and that's why the width has shrunk. So let us take in the p side, previously the width was xp0 in equilibrium, now it reduced to xp, right? So the excess positive charge or extra hole, which is denoted by qpd in this case, can be given by q into xp0 minus xp into Na, that is acceptor ion concentration, into the cross sectional area A. Now this is what is your extra hole qpd. Now if you want to figure out the capacitance associated with this charge, then your capacitance will be dqpd by dV, that is derivative of the same thing with respect to voltage. This particular capacitance is known as C depletion, that is the capacitance in the depletion region. So if you do the derivative, you will find it is minus q into Na dxp by dV. Now if you put the value of xp here and do the calculation, you can figure out what is the expression for the C depletion. However, without doing this also, very easily you can understand the value of the C depletion, because here we have the charges that are separated by xd, that is depletion width, and as both of these charges are acting as a parallel plate capacitor, then you can figure out the capacitance associated with this is nothing but epsilon A by xd. A is the cross sectional area, so the cross sectional area is into the plane. So this is the kind of cross sectional side view. So the cross sectional area is into the plane. So this particular A is the cross sectional area. Okay, and both these extra charges here can be considered as a parallel plate capacitor because they are charges separated by a distance xd. So these charges can be considered as a sheet of charge because this length will be very, very small. So you can consider this as a parallel plate capacitor, and accordingly we will give the expression for the C depletion, which is epsilon A by xd. Even if you do the analysis after putting the expression of xp in this equation, you will find a similar equation. You can do it in your home, but in a much simpler way also you can figure out the depletion capacitance, which is epsilon A by xd. Now, these are due to space charges, that is in the space charge region or depletion region. Now let us see in the quasi-neutral region. Now in the quasi-neutral region, the majority of the current is due to diffusion, right? So these particular charges contribute to the diffusion current, and hence we call it a diffusion capacitance. Now to figure out the diffusion capacitance, the expression would be dqp plus qn divided by dv. Now here you kindly see or you consider that the values of qp and qn are only magnitudes. We don't consider the sign associated with the charges. Okay, even these two are charge wise different. One is positive charge, another one is negative charge. We only will consider the magnitude of these charges. Okay, so your diffusion capacitance will be d into qp plus qn divided by dv. Now your qp plus qn, this particular area defines the qp and this area defines the qn. However, one can question that how come these charges, these are majority carrier charges, how come these charges participate in the diffusion current? So please try to understand, in this case the charges here is equal to the charges over here. So both charge magnitude wise, this area and this area is constant. That's why we consider qp plus qn rather than considering both of them. Okay, so that's why your expression is dqp plus dqn divided by dv. Now if you put the expression for the qp, which is nothing but q into delta p lp into a, right? So q into delta p means, if you look at this is your delta p, if you take this is your lp, right? So the charges will be nothing but either this area or the area under this curve. Okay, so you will find an expression of this kind, and for the sake of simplicity you can take qn is much less than qp because the doping in the p side is much higher than that of the n side. That's why you can neglect the qn. So you will have an expression of this type, so d into delta p by dv into qlpa. Now put the value of delta p, which is pn0 b by vt e to the power b by vt minus 1. So you will have an expression of this, that is q lpa delta p by vt, because in this case you can neglect the pn0 because your del p will be much higher than pn0 under forward bias, that we already have seen. And the current, the forward, from the diode theory, the forward current I is nothing but q into a into delta p dp by lp. Now multiply tau in both the sides, expression will become qa delta p lp by tau. Now if you put that particular expression here, from this and this, you will find qa delta p lp. If you replace the value of I, then it is nothing but C diffusion capacitance is I into tau divided by Vt. So this particular diffusion capacitance is actually a function of the current I. So if you do this particular analysis using these two equations, you will lead to an expression which is C diffusion is almost equal to I tau divided by Vt. So this is your diffusion capacitance. So you have depletion capacitance as well as diffusion capacitance. Now you also can see that this particular nature of the current we take as exponential, and that we already have discussed from the continuity equation. So if you solve the continuity equation and take this delta P as and consider this delta P by del T as approximately equal to 0, you can very easily find the exponential nature of the current, and that is what we actually used. So that is the reason behind the exponential nature. So your diffusion capacitance will be I tau by Vt. Now in reverse bias, this delta P is negative and almost equal to this Pn0. So these two will cancel out, and you will find that reverse bias, your diffusion capacitance is almost 0. If your reverse bias voltage is more than 3 times Vt. If it is less than 3 times Vt, then maybe a negligible amount of diffusion capacitance you may get. However, usually the applied reverse bias voltage is more than 3 times Vt. So you will find that the diffusion capacitance is 0 under reverse bias. Now if you summarize, you will find under forward bias you have a resistance which is equal to Vt by I, and for a milliampere current the value is at ohms. You have a diffusion capacitance which is I tau by Vt. The value usually lies between nanofarad to microfarad. For a larger forward bias it may be larger. So usually it is in between nanofarad to microfarad based on the forward bias applied. And then you have a depletion capacitance which is epsilon A by Ht. Now for moderate forward bias, if the forward bias is moderate in nature, then your diffusion capacitance is much higher than depletion. So you can neglect the depletion capacitance. However, there is a depletion capacitance present in the system. And under reverse bias, you will find your depletion capacitance is epsilon A by Ht, and there is no resistance component because the value of R is very high, and we already have seen that the diffusion capacitance is almost equal to 0. That's why under reverse bias, a PN junction diode can be used as a voltage variable capacitor, because this only acts as a capacitor. And why it is voltage variable? Because if you put the value of Hd, that is here, we already have seen the expression for Hd. If you put the expression for Hd and then if you do some arrangements, you will find 1 by C depletion square is approximately equal to 2 into Vr plus psi naught divided by epsilon S square Q Nd. So in the Hd, we have taken this value as 0 because Na is much higher than Nd for P plus N junction. And then if you replace those values over here and take a square of it, you'll find that this depletion capacitance is actually a function of Vr. Now this depletion capacitance is also known as junction capacitance in certain cases. You'll find in certain literatures it is written as junction capacitance. And this particular capacitance is a function of Vr. That's why it is called voltage variable capacitor. So this reverse bias diode in some cases can be used as voltage variable capacitor. The usual value for this capacitance is in picofarad. If you consider a 0.32 into 0.32 mm square of area for the PN junction. So it depends on the area, because you can find that the cross-sectional area is a parameter here. So for a 0.32 into 0.32 mm square, you will find the range of that junction capacitance is around picofarad.
So we have seen what is small signal model and why small signal model is important. So it's just a circuit consideration, but we have seen why small signal model is important and how we actually get that small signal model. We also have started discussion on diode capacitance. We discussed why diode capacitance is important and how does this concept comes into the picture. How does this concept influence the entire semiconductor physics inside PN junction diode? And we have also figured out what is the expression associated with it. So in this lecture, we discussed both of these concepts fairly in details. Let us conclude this lecture today. We will go through other concepts in the coming lecture. Thank you for your attention.